Hello. If you have any previous experience writing code, you probably realize that logic is crucial for any programming effort. And if you don't, I'm sure you will soon learn it. In this module, we discuss two flavors of logic, Boolean logic and bitwise logic. Our previous presentation introduced Boolean logic, and you should watch it first. This presentation will concentrate on bitwise logic, and the agenda is as follows: bitwise operations and their use, tables of truth, and the binary adder. Let me start from a little reminder, a slide that recently appeared in one of the lectures, Anatomy of a Computer Word. In this presentation, we will not use words of that length. We will just use words of the length of 8 bits, but the essential points here are that bits in a word are always counted from the right side to the left side, and we always start from bit number 0. In C++, we have altogether 6 bitwise logic operators. Do not confuse them with very similar, sometimes Boolean logic operations. Bitwise operations act on each bit separately, and this makes them very different. There are two operations, AND and OR, which are particularly similar to their corresponding Boolean counterparts. The difference is that Boolean operators use double ampersand and double vertical line symbols, and in case of bitwise operations we just have single symbols. There is another operator XOR, which does not appear in Boolean logic, and not operator, which appears in Boolean logic, but at least the symbol here is definitely different. Just as a reminder, not operator in Boolean logic is an exclamation mark. We also have two other operations, right shift and left shift operations, which are of less importance for us, and they have no counterparts in Boolean logic. This slide shows the definitions of 4 most important bitwise operations, so actually all operations apart from left and right shift, AND, OR, XOR, and NOT. For example, the AND operator is defined in this way that 0 and 0 equals 0, 0 and 1 equals 0, 1 and 0 equals 0, 1 and 1 equals 1. It is a bit similar to binary multiplication, but first of all, it's very similar to Boolean AND operator, if we only notice that 0 is equivalent to false and 1 is an equivalent to true. So false and false is false, and so on. But the big difference between bitwise logic and Boolean logic is that bitwise logic does all these operations on consecutive bits. So for example, we can have two numbers, and to discover what kind of operation it is, we have to look into the binary representation of these numbers. So if we have two binary numbers like this, and we apply the bitwise AND operator on this, the result will be as follows. We start from, of course, the rightmost or least significant bit number 0. 1 and 1 is 1. 1 and 0 is 0. 0 and 0 and 1, sorry, is 0. 0 and 1 is 0. 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0, and 0 and 0 is 0. So this is how bitwise operations are performed. How this could possibly be useful? Here is one simple example of the application of a bitwise AND operator. Imagine that in your program you have to test the fifth bit of a word. What it means, you just need to find out whether the bit number 5 in your program is set to 0 or set to 1. The way to do it is to create a special number called a mask or a binary mask, which has a very special binary representation. It contains zeros at every position, apart from the bit positions that we want to test. So in our case, this is a 1 at the 5th bit. Just as a reminder, bits are counted from 0 and from right to left, so it's bits 0, 1, 2, 3, 4, 5. This is our mask. Now we can apply the bitwise AND operation on the number we test and the mask we have created on the basis of the set of bits that we want to test. So 1 and 0 is 0, but actually as long as we have zeros in the mask, we can just write zeros in the result, because if you look at this table here, if you apply the bitwise AND operation to any operand and 0 and 0 is 0, 1 and 0 is 0, so the result will always be 0. So anything and 0 is always 0. So I have 0 here, 0 here, 0 here, 0 here, also 0 here and 0 here. And for the remaining bit, which is the bit we are testing, the bit number 5, this is 1 and 1, which gives 1. And this is the result of the testing. Now, how to interpret the result of the test? If the result value is not 0, this means that the tested bit was set. And this is because the only possibility for the result of bitwise AND operation to be 1, so to be different than 0, is that both operands were 1, so the tested bit was also 1. All other bits are zeroed on the power of the mask. But what if the tested bit had originally the value of 0? So let's take a situation like this, a number with a 0 at the 5th bit, and let's apply the mask created similarly as exactly the same way as previously. And again, we can put zeros everywhere where we have a 0 in the mask. And here we have 0 and 1. 0 and 1 is 0. So as you can notice, the meaning of this mask is wherever we have a 0, we can put 0 in the result. Wherever we have a 1 in mask, then we can copy the original digit from the tested number to the result. But one clear thing here is also that in this case, if the result is equal to 0, then the tested bit is clear. Bit testing is a very powerful operation, and it even allows for testing multiple bits at the same time by providing a mask that has multiple bits set at 1. But what other operations we can do using bitwise logic operations? First of all, if you think about it, computers operate on words, integer numbers, float numbers, but not on individual bits. So even if all that looks a bit like a trick, this is really the only way in which a programmer can access individual bits. So what kind of bitwise operations we can use for manipulating individual bits? Let's imagine that we have an 8-bit register, and let's store example number in this register like this, 01100011. So the first operation that we already know about is the test. Check whether a particular bit has a value of 0 or 1. And let's imagine that we do it for 4 different bits at a time. at the bit number 0, the bit number 2, the bit number 3, and the bit number 5. The test operation is basically to get rid of all other bits apart from the ones that we are really interested in. But of course, what we end up with is not a binary number with holes, it's a binary number with zeros in those corresponding places. So the test operation is basically changing all not interesting bits into 0, and then we can check various things about the part that remains. So that's one possible operation, the test. Another important bitwise operation is so-called set. If you say set a bit, this is usually meaning set a bit to 1. You can use both forms, set or set to 1. So what does it mean, set to a bit to 1? It's we still work on the same selection of bits, so bit number 0, 2, 3, 5, and now we will set consecutive bits to 1. Bit number 5 will remain intact, but bit number 3 will be switched to 1, bit number 2 will be switched to 1, and bit number 0 will remain intact. Done. That's the set operation. Next operation is reset. Reset means the same thing as set to 0. So we will now write zeros into our selection of multiple bits. So bit number 5 will change from 1 to 0. Bits number 2, 3 and 2 will remain intact, and bit number 0 will change its value to 0. And the final operation here is called toggle. Toggle will change zeros to 1 and 1s to 0. So bit number 5 will change from 1 to 0. Bit number 3 will change from 0 to 1. Bit number 2 will change from 0 to 1, and bit number 0 will change from 1 to 0. Let's have once again a quick look at the bitwise AND operator and its associated operation bit test. But this time we will test multiple bits like bit number 0, bit number 2, number 3, and number 5. We also have this sample number, but please note that whilst programming, you will not know what number you are testing, because the point of the whole method is to provide testing algorithm for any potential number. But you will know which bits you want to test, and therefore you can construct a binary mask like this one, where we have ones at the positions corresponding to bits being tested, so at the position 0, 2, 3, and 5, and zeros everywhere else. Performing the bitwise AND operation on this, we get 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 1 is 0, 0, 0, 0, 1 and 1 is 1, 1 and 0, 0, and 0 and 0 is 0. This is the result of the test. Now the question is how exactly we should interpret this result, this number, particularly in the situation that we have several bits that we are testing. So, if the result would be equal to 0, this must mean that all bits in the tested number are clear or are also equal to 0. If the result is not 0, different from 0, then some bits are set, and this is the case here. If the result would be equal to the mask, which is not the case here, but if it was, this would mean one thing, that all bits are set, or all bits, tested bits, all the bits that we are testing are equal to 1. And if the result is not equal to mask, then this must mean that some bits are clear. Now let's go to the OR, bitwise OR operator, which can be used for setting bits or writing ones into the selected bits. So here the task is to set bit number 0, 2, 3, and 5 to the value of 1. As you can see in our sample number, not all bits are 1, so the result here should have ones written at every tested position. We create a similar mask. Actually, it's exactly the same mask as previously, as the mask used for testing, and now performing the OR operation. 1 or 1 is 1, 1 or 0 is 1, 0 or 1 is 1, 0 or 1 is 1, 0 or 0 is 0, 1 or 1 is 1, 1 or 0 is 1, and 0 or 0 is 0. You can notice one interesting thing. Wherever you have a 1 in the mask, the bit gets set. Okay, whatever was its original value, all these red bits here are set to 1. And if we have a 0 in the mask, then nothing is done with the original, with the input bit, so it's not changed. Therefore, the mask means that we can choose individual bits to be set to the value 1. And a very similar situation we have with the XOR operator, which by the way, XOR stands for exclusive OR. In logical terms, this means either one or the other. Okay, so if we have none of them, like 0 XOR 0, the value of XOR operation is 0. If we have either 1 here or 1 here, the value will be 1. But because it is either this or that, not together, 1 XOR 1 is 0. And the XOR operator is used in bitwise operations to toggle selected bits. So once again, we create the same mask as previously with bits number 0, 2, 3, and 5 set. And if we apply the XOR operation, I will do it quickly now, on individual bits, we will get a situation in which every position that corresponds to a 1 in a mask got a toggle. So 1 became 0, 0 became 1, another 0 became 1, and this 1 became a 0. And as previously, a 0 in the mask means do nothing. We have done a toggle, a set, a test. We are clearly missing the clear bits operation. So what to do in order to store a 0 into selected bit positions. And for this purpose, we'll once again use the AND bitwise operator, but very importantly, with a specially modified mask, with a negated mask. Negated mask is a mask in which we replace all zeros with ones and all ones with zeros. So instead of this mask, we'll get this negated mask. This mask can be also created by putting zeros in at every interesting position. So 0 at position 0, 0 at position 2, 0 at position 3, and 0 at position 5, and ones at every other uninteresting position. So this is a mask which is directly opposite to the mask we used previously. But the AND operation will be exactly the same as previously. So 1 and 0 is 0, 1 and 1 is 1, and so on. 0s, 0 and 1, 1, 0, 0, 1, 1, 1, 0, 1, 0. This is the result, and in this result we can notice a little bit different thing. Wherever we have a 1 in the mask, in our negated mask, the 1 now means do nothing, and 0 in the mask means clear this bit. Obviously, using this mask in a different way than we did previously, and finding this negated mask must be a kind of inconvenience, but don't we have one more bitwise operation left? Yes, we do. This is the not operator. Not operator, like in not 0 is 1, not 1 is 0. We can use this operator to negate all bits, for example, to negate all bits in our mask. So we can now write our usual mask, so putting 1 in interesting bit positions and zeros everywhere else, and then apply the not operator on this mask. So this is not 1, this is not 0, not 1, not 1, not 0, not 1, not 0, not 0. And this creates the negated mask. This opens the way to some improvement to our procedure for clearing bits, because we can now use the combined AND NOT operator. So the AND operator and NOT operator used at the same time. So once again, let's clear bits 0, 2, 3, 5 in a new way. And this new way is based on our usual mask, so not a negated mask. And the use of the double AND NOT operator will first of all negate our mask, creating a negated mask, and then apply the AND operation on the actual number that we are testing, creating the result like this, in which one position in the mask corresponds to the clearing of a bit operation, and 0 position in the mask, as in most cases before, means simply do nothing. So wherever you have a 1 in the mask, this will clear the bit, and wherever you have a 0 in the mask, it will keep the bit intact. Some more examples, and these examples are written in C++. So the first example is test the 0th and 1st bit. But the test makes only sense if you use this test inside the if statement. So this is a C++ if statement. If A and OX03. Why OX03? Because this is the test of the 0th and the 1st bit, and the diagram on the right side of the screen shows the entire binary number. The point is that C++ does not accept binary notation in the source code. So you have to convert binary at least into hexadecimal code. You could also convert it to decimal code, but this is always a bit of headache. So with this type of exercises, we would usually prefer hexadecimal conversion, because hexadecimal conversion is much simpler. If you notice the fact that if you take any length of binary number and you divide it starting from the right side and going to the left, if you divide it into groups of 4 bits, then you can consider each group of 4 bits separately as a single hexadecimal digit. And now, working along these groups from the left to the right, so a little bit untypically, you can just read hexadecimal directly from binary. So 0000, it's a hexadecimal 0. 0011, it's a hexadecimal 3. Okay, if you remember binary code, you should soon notice that 0011 is 3. So 03, that's the hexadecimal value of this binary mask. The second example is about setting the 1st, 2nd, 6th, and 7th bit. And we have indeed 1st, 2nd, 3, 4, 5, 6th, and 7th bits shown here. In C++, in order to make any point for this operation of setting bits, you not only have to provide the notation for A or the value of the binary mask, but this value has to be stored in a variable. So it makes sense to write something like A equals, actually equals means becomes, okay? So A becomes A or OX C6. Why this is C6, I'm leaving for you. You have the diagram here. Please remember 2 groups of 4 bits, 1 digit and the other digit. If you just decipher these digits from binary to hexadecimal, you get C6. The next operation is reset bits, number 3, number 4, and number 5. So it's A equals A and not OX38. So please note that we have used here this double operator for resetting bits, and not, okay? And not A and not 0x38. Thanks to this, we can use just a straight bit mask and not necessarily a negated bit mask. And this time I will help reading the hexadecimal value. The first group of 4 is 0011. It is binary representation for 3, so the first digit is 3. And the second group of 4 is 1000. It's a binary representation for 8, and thus the second hexadecimal digit. And the last example here is toggling bits. We will toggle the second bit, the fourth bit, and the sixth bit. So the first hexadecimal digit is 0101. This stands for 5. The second hexadecimal bit, digit is 0100. This stands for 4. So the toggle bit code is A equals A XOR 0x54. The next slide will be a repetition from the previous lecture because it's so substantially, essentially important. Don't confuse Boolean logical operators and bitwise logical operators. Remember, Boolean logical operators are like double ampersand, double line, and bitwise logic operators are single ampersand, single vertical line. The not operator is completely different for Boolean and for bitwise. It is important because in the Boolean universe, 1 and 2 will be understood by the compiler as 2 different representations of the logical true. So this is actually true and true. True and true gives true. So 1 and true Boolean, in terms of Boolean, is true. But bitwise, 1 and 2, I propose even to write it down as binary representations. 1 and 2 is 0. Okay, 1 and 2 bitwise is 0. So these two operations, very similar in the terms of C++ notation, produce different results. I will now briefly discuss the 2 remaining binary operators, but they are of less importance for us in games development. It's still nice to know about them, and the crucial information for you, they will not appear in the in-class test. So the first operator is left shift operator. It looks like this: A left shift 2, for example. And it does exactly what its name says. So it takes all the bits of a binary representation of a number, for example, this number, and shifts all these bits to the left. Okay, so that's shift by one position. For example, this one goes to here. And then because it is a shift by two positions, it does it again. All right, so it creates this number here. I provided here additionally a hexadecimal representation and decimal representation of this operation. So from a number 41, after the first shift we get 82, and after the second shift we get 164. Effectively, this is multiplication performed, and in fact, this is the fastest way in which we can do multiplication in C++. The problem is that we can, in this way, only multiply it by 2 and powers of 2. So in this case, this is multiplication by 4. 41 times 4 is 164. Okay. Please note that the most significant bits are dropped. In this case, it wasn't a problem because the two most significant bits were zeros. So where they are dropped, it doesn't affect the value of this operation. But let's have a look what happens if we shift 3 times. 1, 2, 1, 2, now 3. Let's have a look what happens in case of a shift by 3 positions. So that's the original value, shift once, shift second time, shift third time. So this bit with the value 1 after the first shift was here, after the second shift was here, and after the third shift disappeared. And also please look what happened with our decimal values. 41 became 82, became 164, became 72. So this is numerical overflow, and left-right shift operators do not check for any errors, any numerical overflows. So it's a fast way to get multiplications of a number, but also not the safest way. And we also have the right shift operator, which works the same way, but moves everything to the right. So this is shift by 2 positions to the right, 1, 2. From 165 we got 41. Please note that the rightmost, the least important bit has been lost after the first shift. Effectively, this is division. Again, performed twice. So you can divide numbers by 2, by 4, by 8, and so on, very, very quickly, but also least significant bits will be dropped. Left and right shift operators are the most efficient way of multiplying numbers, but limited to the powers of 2. The final topic discussed in this lecture are the tables of truth. Tables of truth were discussed in the previous part of this lecture on Boolean logic. So here we just have a few simple tables for A and B, A or B, A XOR B, not A, and the combined operator A and not B. But the true reason why I introduce these tables are the others. And I don't mean the snakes, and actually the snake you can see in this photo, and which I photographed a few years ago in the south of France, it's not an adder. It's very similar to adder, but it's another type of a water snake. But never mind, adder for us is a electronic device for adding two numbers. And we discussed some others in the binary lectures some time ago. But here I propose a table of truth for a half adder. Half adder is just a circuit that takes A and B, all possible combinations of A and B, so 0, 0, 0, 1, 1, 0, 1, 1. And now the value of A plus B is 0, 1, 1, 0, depending on the combination of operands. And we also have the value of C. C is the carryover. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but 1 plus 1 is in fact the binary 1, 0. So the value of the bit will reset back to 0. A plus B will be equal to 0, but it will also generate a carry over to the next bit position. So as you can see, addition can be coded in the form of a table of truth and can also be shown as bitwise logic functions. If you look at A plus B, it may become quite clear that A plus B equals A XOR B. Using the XOR bitwise operation, we can mimic, or we can provide the correct formula for binary addition. And the formula for the carryover bit is A and B. So these two very simple formulas, A XOR B and A and B, give us the bitwise logic-based recipes for binary addition. I also have here a full adder. Full adder also takes into consideration the carry from the previous binary position. For example, 0 plus 0 is 0, 0 plus 1, and so on. But 0 plus 0, if the carry from the previous position was 1, the result will be 1. 0 plus 1, if there is a value carried over from the previous position, will be 1, 0, so A plus B bit will be 0, and the carryover will be generated. Similarly, for 1 plus 1 plus carryover from the previous position is 1, 1, so the value of the sum, the value of the added value will be 1, and the carryover to the next position will be 1. The formulas for the full adder are a little bit more complex, so this one is quite reasonable. A plus B is just A XOR B XOR the carry from the previous position, but the carry to the following position to the next position is a little bit more complex, but it's still possible to present in the form of a set of bitwise logic functions. Adders in real computers are normally put into sequences, so you can provide a number A, giving its bits here A0, A1, A2, A3, and so on, and the number B, B0, B1, B2, B3, and our system of these adders will generate the sum of A and B here S0, S1, S2, S3. All these adders will be connected through the carries, so the carryover generated from bit 0 will be transmitted as the input for the full adder for the bit number 1, and so on, so on, so on. You can create sequences of the length that you need in any case. So this is a 4-bit adder, but you can easily now imagine 8-bit, 16-bit, 64-bit adder. This is how addition is built in modern computers. The take-home message from this is that computers arithmetics, like addition, is built upon the bitwise logic operations. So as much as binary digits are the primary building blocks for storing information in computers, the bitwise bit operations are the primary language of computers, actually the language in which things like addition and all other calculations are made. And on that bombshell, the lectures on logic of computers will conclude. Thank you for watching, and don't forget to watch our practice videos published alongside these lectures. Thank you.